Okay, now let us see the designing of IIR filters. So we have two filters here. One is Butterworth, another one is Chebyshev. And in both the filters we have type 1 and type 2 as subtypes. So these type 1 and type 2 are similar in most of the aspects. So let us start with Butterworth first. So in Butterworth filter, the problem will be stated as del 1 less than or equal to h into e power j omega less than or equal to 1, h into e power j omega less than or equal to del 2, 0 less than or equal to omega less than or equal to omega 1, omega 2 less than or equal to omega less than or equal to pi. This is how the problem will be given us. So here we have to find the values for del 1, the values for del 1, del 2, omega 1 and omega 2 will be given in the problem. And let us start how to design a filter using type 1 Butterworth. Okay. So the designing involves 5 steps. Step 1 is to determine H frequencies. Ohm 1 and ohm 2. These are the symbols that represents the H frequencies. So ohm 1 is given as 2 by t tan omega 1 by 2, and ohm 2 is given as 2 by t tan omega 2 by 2. This is in case of bilinear transformation. And ohm 1 is given as omega 1 by t and ohm 2 is omega 2 by t. This is for impulse invariant. We have already seen 3 methods to convert analog to digital filter: approximation of derivatives, bilinear transformation and impulse invariant. Out of these 3, only these 2 types are used for filter design. Approximation of derivatives is not employed in designing the filters. And the method which has to be used to design the filter will be specified in the problem. So you can use the formula directly. And this particular process is called as pre-warping. And we can see about warping effect in detail later. And so we know the value for omega 1 and omega 2 from the given equation. So we can substitute omega 1 and omega 2 in this equation and we can find the value for ohm 1 and ohm 2. We can use any one of this method depending upon the need. So step 2 is to find the order of the filter, order n of the filter, and n is given as greater than or equal to 1 by 2 log 1 by del 2 square minus 1 divided by 1 minus del 1 square minus 1 whole divided by log of omega 2 minus omega 1. So ohm 2 minus ohm 2 by ohm 1. So here we know the value for del 1 and del 2 from the given equation, and we know the value for omega 1 and ohm 2 from the step 1. So whatever you find in step 1 will be applied in step 2. So if anything goes wrong in step 1, the forthcoming steps will go wrong. So please be careful while substituting the values. And so we will be finding the value for n here, and look at the equation here. N is always greater than or equal to. So in case while substituting the values, and if you get some answer like n is greater than or equal to 1.003, or if you get some values like this, it has to be always rounded off to the next available integer. So this n has to be approximated as 2 and not as 1. Though we have 2 zeros here, it has to be approximated as 2, because the higher the order, the better the output. So always the formula is n is greater than or equal to. Sometimes we may get the value for n is greater than or equal to 2.6, something like that. So in such case, we can approximate it into 3. So whatever the value for n, if even there is a 0.001 variation, then you can approximate to the next available value. So in step 3, we'll be finding cutoff frequency. To find cutoff frequencies, ohm C. So ohm C is given as ohm C is equal to ohm 1 by del 1 square minus 1 the whole power 1 by 2n. So in step 2 we'll be finding n. So that particular value has to be substituted here, the approximated value. So we'll be finding omega C here. Then in step 4 we'll be finding the analog transfer function. H of S, because we'll be designing only analog filters using Butterworth and Chebyshev. So after designing these analog filters, we have to convert into digital, which we have seen earlier, and that will be the last step here too. So in step 4 we'll be finding the transfer function H of S. So we have two formulas for H of S depending upon the value for n. If n is even, like 2, 4, 6, and it goes on. If the value for n is even, then the formula for finding H of S is given by H of S is equal to pi k equal to 1 to n by 2. Pi represents the multiplication function. It is something similar to summation. If in case of summation, we'll be adding the terms that is given on the right hand side. In case of pi, we have to multiply. It's a very simple operation. Okay, so it is given as pi of k equal to 1 to n by 2 bk omega c square by s square plus small bk omega c s plus capital ck omega c square. And in case if n is odd, like 1, 3, 5, 7, it goes on, then we have the equation as H of S is equal to B naught omega c by S plus C naught omega c pi of k equal to 1 to n minus 1 by 2 to bk omega c square by s square plus bk omega c s plus ck omega c square. So you can use these you can use this formula directly to find the value to find H of S. So here capital BK is always equal to capital CK, and which is also equal to 1. In case of Butterworth filter, it is always equal to 1. So obviously B naught and C naught will be also equal to 1. So we know the values for B naught, C naught, BK, CK, and S is the S is for analog transfer function, so we need not substitute any value for S. We can leave it as such. So S will be carried out throughout the equation. So we know omega C from the previous step, and the only unknown term left out now is small bk. Small bk is given by 2 sine 2k minus 1 pi by 2n. So this is a formula to find bk. So here, when n is equal to, so assume the value for n is 2, so it is even. So n is 2 and it is even. So here we substitute 2 here, so 2 by 2 1. So k equal to 1 to 1. So the value for k will be 1. So it is b1 omega c square by s square plus b1 omega c s plus c1 omega c square. So whatever the value for bk and ck, it is going to be 1. So we can take off we can substitute 1 for here. And for finding small bk, we have to use this formula. So that is b1 is equal to 2 sine 2 into 1 minus 1 into pi by 2n. So if we solve for this, you will get the value for bk and you can substitute here. Sometimes if the value for if the order of the filter is 4, so in such case we have to substitute 4 here. So 4 by 2 is 2. So k varies from 1 to 2. So first we have to find for b1, small b1, capital C1, and then you have to find for capital B2, small b2 and capital C2. And those two equations has to be multiplied with each other. So that is the function of pi. And in step 5 we'll be dealing with the concept which we have seen earlier, conversion from analog to digital, that is from h of s to h of z. So here we have two methods for conversion. First one is bilinear transformation, and second one is impulse invariant. So in bilinear transformation, wherever you find s in the equation, in the h of s, you will be replacing s with 2 by t 1 minus z inverse by 1 plus z inverse. And for impulse invariant, if you find the equation in this format, you can replace it directly with 1 by 1 minus e power pkt into z inverse. So this is the design procedure for designing a Butterworth filter. So we have seen how to design a Butterworth filter type 1. Now we will see with type 2 Butterworth filter. Type 2 Butterworth. There is no much difference between Butterworth filter type 1 and type 2. Only the difference is the way in which the problem is specified. For type 1, Butterworth filter, the problem will be specified as del 1, del 2, omega 1 and omega 2. These values will be given directly. But in type 2, these values will not be given directly. So we have to find the values for del 1, del 2 and omega 1, omega 2 before proceeding to the problem. So in type 2, usually the problem will be specified in values of pass band and stop band. So it will be given like pass band as alpha 1 and stop band as alpha 2 in terms of decibel, and pass band frequency as f1 hertz and stop band frequency as f2 hertz. So the problem will be specified only with these terms. So we have to apply certain formulas to find the values for del 1, del 2, omega 1 and omega 2. So once you find the values for del 1, del 2, omega 1 and omega 2, it is similar to that of type 1. So for finding del 1 and del 2, we have a formula. So del 1 is given as antilog of alpha 1 by 20, and del 2 is given as antilog of alpha 2 by 20, and omega 1 is given as 2 pi into f1. So f1 will be stated here, so if you substitute f1 here, you will get omega 1, and omega 2 is given as 2 pi into f2. Sometimes they may give the values for omega 1, omega 2 directly. You can categorize, you can identify those equations like with the help of these units. If it is given in terms of hertz, obviously it is frequency. If it is given in terms of radian per second, then definitely it is omega 1 and omega 2. And always the values for omega 1 and omega 2 ranges from 0 to pi. So with the help of the values of omega 1 and omega 2, you can find which one is pass band and which one is stop band. Sometimes pass band and stop band will not be specified in the problem. So in such case, we can use the value of frequency or the value of omega 1 to find which one is pass band and which one is stop band. So now we have found the values for del 1, del 2, omega 1 and omega 2. So hereafter everything, all the rest will be similar to that of type 1. You have to use those 5 steps. Step 1 to find H frequencies, then you have to find order, then you have to find the cutoff frequency, then you have to find the analog transfer function, and finally you have to convert the analog function into analog filter into digital filter. So here we have to note that while taking the antilog, always the value of alpha 1 and alpha 2 should be in negative terms. Sometimes in the question they may specify the value of alpha 1 as 3 dB and alpha 2 as 10 dB. So in such case, what you have to do is you have to take del 1 as antilog of minus 3 by 20 and del 2 as antilog of minus 10 by 20. Always there should be a minus prefixed in front of alpha. Sometimes in the question they may specify the value as minus 3 dB and minus 10 dB. In such case, we can use those values directly as minus 3 by 20 and minus 10 by 20. If it is not given, if the negative sign is not specified in the question, we have to include a negative sign here. Only then the design procedure will be smooth. And hereafter we have to follow the type 1 procedure as it is from step 1 to step 5. So that's it for Butterworth filter. Let us start with Chebyshev in the next video. Okay, now let us see the design procedure of type 1 Chebyshev filter. So here, similar to that of Butterworth filter, even in Chebyshev filter we have a similar kind of approach. Here del 1 is less than or equal to h e power j omega less than or equal to 1, h into e power j omega less than or equal to del 2, omega 0 less than or equal to omega less than or equal to omega 1, and omega 2 less than or equal to omega less than or equal to pi. This is how the problem will be stated, similar to that of Butterworth type. So here del 1, del 2, omega 1, omega 2 are the terms which is given directly in the problem. So with these terms we can straight away go to the design procedure. So it involves steps which are similar to that of Butterworth. So step 1 is to determine H frequencies, ohm 1 and ohm 2. So here ohm 1 is given as 2 by t tan omega 1 by 2 and ohm 2 is 2 by t tan omega 2 by 2. This is for bilinear transformation. And ohm 1 is equal to omega 1 by t and ohm 2 is equal to omega 2 by t. This is for impulse invariant. And step 2 is to find order n of the filter. And n is given us, n is greater than or equal to cos h inverse of 1 by epsilon into 1 by del 2 square minus 1 the whole power 1 by 2 divided by cos h inverse of omega 2 by omega 1. So here, so this is hyperbolic cos inverse. So to obtain cos h inverse, what you have to do is, in the calculator, press hype button, which represents hyperbolic function, hype plus cos inverse. So normally to attain cos inverse, we'll be using shift plus cos. So using these three combinations, we can obtain cos h inverse. And in certain natural display calculators, if you simply press the hype button, it will give you an option to select various hyperbolic functions like cos h inverse, cos h inverse, sin h inverse, along with the numbers prefixed in between before that. So you have to select the appropriate one for selecting cos h inverse. So if you are going to use fx991ms, you can follow this method: hyperbolic and shift plus cos. These three keys will bring out cos h inverse for you. And next, so here we know how to find cos h inverse, and we have the value for del 2, which is given in the problem itself. So epsilon is the unknown value here. So epsilon is given by 1 by del 1 square minus 1 the whole power 1 by 2. So we have found epsilon, and you know the values for omega 1 and omega 2 from the previous step. So substitute everything, you will get n, and as I stated earlier, n is greater than or equal to the obtained value. So even if you get 1.0006 or something, whatever it may be, even after having 3 zeros after the decimal point, it has to be always rounded off to the next integer, that is 2. Similarly, if you are getting n is something like 2.4 or anything, or 2.3, anything has to be rounded off to the next available integer, that is 3. Clear? Okay. Now next step is to find the cutoff frequency. Cutoff frequency omega c. Okay, here cutoff frequency is given as omega c is equal to, the cutoff frequency is nothing but the edge frequency of omega 1. So omega c is equal to omega 1, that will be the formula. And for step 4 is to find h of s, that is the analog transfer function. So what is h of s? H of s is given by pi of k equal to 1 to n by 2 bk omega c square by s square plus small bk omega c s plus ck omega c square. This is for when n is even, it is like 2, 4, 6, any even values. For any even values of n, this will be the formula. And for when, if n is odd, we have a formula of h of s is equal to b naught omega c by s plus c naught omega c phi of k is equal to 1 to n minus 1 by 2 bk omega c square by s square plus bk omega cs plus ck omega c square. So this is when n is odd. So here we have unknown terms bk, ck, small bk, b naught and c naught. So here first let us find the value for small bk, because all the other values will be derived from bk. So bk is given as 2 y base n sine 2k minus 1 pi by 2n. So here we have introduced a new term called y base n. So this y base n is given as 1 by 2 1 by epsilon square plus 1 the whole power 1 by 2 plus 1 by epsilon the whole power 1 by n minus the same function again 1 by epsilon square plus 1 whole power 1 by 2 plus 1 by epsilon the whole power minus 1 by n. So the entire term will be divided by 2, that's why I have added 1 by 2 in the front. So now we have y of n. So with the help of y of n we'll be finding bk, and next we have to find capital BK, capital CK, and C naught and B naught. And always C naught is equal to y base n. So the moment you find the answer for y of n, you can substitute it for C naught. So C naught is going to be y of n. Next. And we have a formula for CK. CK is given by plus cos square 2k minus 1 pi by 2n. And again it's in the form of cos square theta. So we cannot find cos square theta directly in the calculator, so we have to convert this into some other function. So we have to use the formula of cos square theta is equal to 1 plus cos 2 theta whole divided by 2. So by applying this formula we can find the value for cos square theta. So after finding CK, there is a relationship between CK and BK. So which is nothing but if n is even, then a by 1 plus epsilon square the whole power 1 by 2 is equal to pi of k is equal to 1 to n by 2 to bk by ck. So you can find the value for CK using this formula, and after finding the value of CK you have to substitute here. So with this we will be finding the value for BK. We know the value for epsilon, and A is nothing but gain, which is always going to be 1. So A is equal to 1. So we will substitute 1 here, and the CK will come here and BK will stay here. So that will be the value for BK. And if n is odd, then the relationship is given as A is equal to pi of k is equal to 0 to n minus 1 by 2. Please note there is a difference in the limits. It's for in case of even it is k equal to 1, and in case of odd it's 0. Dk by ck. So if you find C0, I mean when k is equal to 0, C0 and B0 will be in this place. So we already know the value for C0, which is nothing but yn. So bk is equal to ck, as a is 1 and we don't have any other term here. So it is going to be bk is equal to ck when k is equal to 0. And you can straight away substitute the value of C0 for B0. And again it's a pi function. Sometimes the order may go up, like if n is 4, then the limit varies from k equal to 1 to 2, because when you substitute n equal to 4 by 2 is going to be 2, so k equal to 1 and 2. So you'll be having two equations here, bk by ck, which is b1 by c1 into b2 by c2. So we'll have c1 and c2. We have, we know the value for c1 and c2 from this formula. By substituting the value for k, you can find the value for c1 and c2. And we'll be having two unknown terms, b1 and b2. So what you have to do is you have to keep these terms here, b1 and b2, and we can take this c1 and c2, multiply it together to the left hand side. So we will have b1 and b2 on the right hand side, and we'll have some other value here. So in such case, what we can do is we can take either b1 or b2 as 1. So we'll get the other value directly. It's simple. So, but in most cases, we won't be having such situation, because normally in these problems, the value for n will be either 2 or 3. So if it is going to be 2, 2 by 2 is going to be 1, so k is going to be 1. And if it is going to be 3, 3 minus 1 by 2 is going to be 1. So k is going to be 0 and 1. And we know the value for C0 is going to be yn. And we need to find only the value for C1, which is pretty simple. And when it's very simple, just like that, which I said earlier, we'll be having two values here. Just keep one value as 1 and take the other value, which is on the left hand side. Okay, so now we have found h of s, and we also derive the formula for finding all the unknown terms. Now the last step is to convert from h of s to h of z. So that is from conversion from analog to digital. So similar to that of Butterworth, we have two types here. One is bilinear transformation, another one is impulse invariant. So in case of bilinear transformation, it is going to be like this. Wherever you find s, so you have to replace it with 2 by t, 1 minus z inverse by 1 plus z inverse. And in case of impulse invariant, wherever you find the equation in this format, 1 by s minus pk, you can replace it with 1 by 1 minus e power pk t into z inverse. And that's pretty much for designing a Chebyshev filter. Okay, next let us start with Chebyshev filter type 2. Chebyshev type 2. It is similar to that of Butterworth type 2. Here the problem will be stated with passband and stopband attenuation, along with the passband and stopband frequencies. So passband attenuation will be given in terms of alpha 1 unit decibel, and stopband attenuation will be given in terms of alpha 2 decibel, and passband frequencies F1 hertz and stop band frequency F2 hertz. Here either they may give in terms of frequency or they may give in terms of omega 1 and omega 2. You have to differentiate frequency and omega with the help of units. So if it is given in hertz, it's going to be frequency, and if it is given in radian or radian per second, it is omega 1. So in both cases we have to use the corresponding formulas. So first we have to find del 1 and del 2 and omega 1 and omega 2 from the given data. Once after finding the value for del 1, del 2, omega 1, omega 2, we can straight away go to the regular type 1 method, just like that of Butterworth filter. So del 1 is given as anti-log of alpha 1 by 20, and del 2 is given as anti-log of alpha 2 by 20, and omega 1, in case if it is not given here, we can find omega 1 with the formula of 2 pi into f1, and omega 2 is 2 pi into f2. And as I have told earlier, always the value of alpha 1 and alpha 2 should be kept in negative. Sometimes if in the question if they have stated as pass band attenuation as 3 dB and stop band attenuation as 8 dB, then while calculating the antilog, it has to be calculated as del 1 is equal to antilog of minus 3 by 20 and del 2 as antilog of minus 8 by 20. Sometimes they may specify in the question as minus 3 dB and minus 8 dB. In such case, you can use those values directly. So, and still the equation will be in the same format. It should be minus 3 by 20 and minus 8 by 20. Always there should be a minus sign in front of the value, in front of the alpha value. Okay. And so we know the values for alpha 1, we know the values for del 1, del 2, omega 1 and omega 2. So now we can straight away proceed to the problem by following the procedure of type 1 from step 1 to step 5. The same procedure we can follow, and that's the end of filter design of Chebyshev.